Okay, in the last video we established that this system that I have up on the board here is Hamiltonian. Now, what that means is that f, the function that's giving me my x prime, is the partial of h with respect to y for some function h of xy, which we're going to call our Hamiltonian function. The level curves for this function are the solutions to the system, because this is going to be a conserved quantity on the system, which means that if I travel around the solution curves, h doesn't change. So its derivative with respect to time as I travel along the solution curves is 0. That's just a stray mark. Okay. All right, g, the function that's giving me my y primes, is the opposite of the partial of h with respect to x. Okay. So I'm going to use this information to try to find h. Now this is going to be almost exactly like what we did when we were solving for exact differential equations. We had essentially formulas for the two partials of our function. Here, this just happens to be the opposite of one of the partials. So it's really the same four-step process. Step 1, I'm going to integrate one of these partials. So I can either integrate f of xy, which is the partial with respect to y dy, or I can integrate the opposite of g of xy, which would give me the partial with respect to h, the partial of h with respect to x. I can integrate that with respect to x. Either one of these should work. I usually just go with this one because I don't have to worry then about changing the sign of things. Okay, this will give me a partial formula for h. So the result is a partial formula for h. I'm going to just write out the rest of the steps as if we've done this as opposed to this. They can easily be modified if we chose to start with this. Step 2. Okay. So if I've integrated f, I've already used the fact that that gives me a formula for the partial of h with respect to y. So I'm going to differentiate with respect to the other variable. So if I integrated with respect to y, I'm going to differentiate with respect to x. Okay. Now, when I integrated here, my partial formula with respect to h would have been something, something, something plus k of x, plus some function of x, because this would be constant with respect to with respect to y. Okay. So when I differentiate with respect to x, I'm going to say the partial with respect to x of blah, 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 plus k of x is equal to blah, blah, blah prime, plus, oh, actually let's not use prime notation there. I'll just say the partial with respect to x of that, because that's a function of two variables, plus k prime of x. Okay. But I can set that equal to the opposite of g of x, because that's also going to give me a formula for this. Okay. So if I set this equal to the opposite of g of xy, then I'll be able to solve for k prime of x. Which, if I've done everything correctly, will be a function of just x. If there are y's in it, that tells me I've done something wrong. Don't keep going. Go back and find your mistake. Once we have that, I think I've got enough room up here to finish this up. Step 3, I'm going to integrate k prime of x dx to get k of x. And then step 4, put the pieces together to get h of xy, that's my Hamiltonian function, set equal to a constant to get the level curves of h, which are the solutions to the system. Pretty cool. Okay, so this part should feel somewhat familiar, although I realize it's been a while since we looked at the exact differential equations. And we do need to modify just a little bit because, of course, our functions are a little bit different. This is what they're equal to. I find it very helpful to write this out once I know the system is Hamiltonian. Okay, so step one, I'm going to say h is going to be an integral of the partial of h with respect to y dy. So I'm going to be integrating x cosine of xy dy. So I'm just going to do a quick u sub. I'm going to let u equal xy, and then du will just be x dy. Well, that's great. That's going to absorb that x. So this becomes the integral of cosine of u du, which is just going to be sine of u plus something that is constant with respect to y, which would be k of x. So then sine of xy plus k of x. So that gives me a partial formula for what h is going to be. Okay. So from step one, I've got that h, keep losing this, h is sine of xy plus k of x. Okay. Step two, I want to say I just got that by integrating with respect to y. Let's do some stuff with respect to x. So the partial of h with respect to x is going to be the partial with respect to x of sine xy plus k of x. That's going to be cosine of xy, chain rule, times the partial with respect to x of xy is just y, plus k prime of x. And here, because k is a function of just one variable x, it's okay to use the prime notation. Okay, I'm going to now say, I know that the partial of h with respect to x was the opposite of g of xy. So, y cosine of xy plus k of x is equal to the opposite of this, which would just be y cosine of xy. Well, that's, sorry, k prime of x. That's awesome. That tells me that k prime of x is equal to 0. Now, that pretty much tells me when I integrate, I'm just going to get an honest-to-goodness constant. But just to go through the rules, just because this is our first time doing it, I would say, okay, k of x is an antiderivative of k prime of x, which is going to be an integral of 0, which is just going to be a constant. I'm just looking for a Hamiltonian function. They're not going to be unique because this constant of integration could be anything that I want, but I'm going to choose the simplest one I can think of. I'm going to choose c equals 0. Okay. And so then step 4, we put the pieces together. So we're going to say h of xy is just sine of xy plus 0. Now be careful. My answer to this question is not the function h. My answer to this question, my solution to this system, are the curves that are the level curves of h. So that would be sine of xy equals k, where k would be an arbitrary constant. Okay, pretty cool. In the next video, I want to talk just a little bit about the sorts of equilibrium points that we can have in a Hamiltonian system. Once we've done that, we'll take a look at finding the phase portrait for this particular system. I know what my solution curves look like. They're just the level curves for this function. So we'll review how would I go about graphing something like that. And then figure out how do I then figure out what the orientation is, because that's just going to give me the curve. But I know that for a phase portrait, I want the orientation of those curves. Okay, so that's where we're going.